Welcome to the Combining Techniques revision session. So in this session, we're going to go through a couple of the questions which are outlined in your worksheet, and we're going to basically go through the way I answer these types of questions. Okay? So first of all, I'd follow the following steps when I answer a combining techniques question, and it really goes through what technique you're going to utilize first and for what reason. So sometimes you're given a empirical formula. Sometimes you need to work it out, and you guys should know how to do that. Anyway, the second step is to look at your mass spectrum. And what you do is you pick the heaviest ion. This heaviest ion is called the parent molecular ion. And refers to the unfragmented ion. Remember that when a molecule is introduced into the mass spec, it's actually in the gaseous state. Then it undergoes ionization. Basically, it's bombarded with a very high energy electron with high enough energy to overcome the ionization energy. Okay, so when it overcomes the ionization energy, it basically kicks an electron out of the molecule, but we don't know whereabouts it kicks it out from. So we just write it in a simplified way as having a positive charge, but it's still in the gaseous state, and we get 2 electrons which come out. Then it could undergo fragmentation. Basically being because this guy tends to be very unstable and further fragments into smaller ions. Now, when you have a look at your molecule, every time there is a covalent bond, there is a chance for it to fragment. It could fragment there, 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 or there. Okay? We just have to make sure that it matches up to the correct mass to charge ratio. So, for example, this ion could fragment into could be like this. And then we would have OH with no charge. Now, this guy will be sucked out by the vacuum, is not read by detector because it doesn't make it there. But this guy is the one that comes up on the mass spectrum. So anyway, your parent molecular ion gives you the relative molecular mass. Remember that if our empirical formula, like our empirical formula for this guy would be CH2O, which actually weighs 16, 26, 28, 30. Now you don't put grams per mole because remember, it's different for different isotopes. So we do count this as 12, and we do count this as 1, and we count this as 16 because they're the most common isotopes. But if you have something like CH3Cl, you will either have CH3 Cl37 or 35. Now these will weigh different amounts. 37 plus 12 is 49, 52, and this will weigh 50. Okay, So basically, that's the way it works for different isotopes. And there'll also be different heights depending on the relative abundance of the isotopes. So you get your relative molecular mass, no units, right? Because it's just relative to carbon-12. So we would get the relative molecular mass for this one, and there'd be a nice peak at 60, and then it would tell us that 60 divided by 30, which is your empirical mass, and you do your relative molecular mass equals 2. So we'd have to times this by 2, getting C2H4O2. And then that would give you your molecular formula. So, the mass spectrum, the heaviest peak is called the parent molecular ion. This gives you the molecular formula. The third step you do is identify bonds and therefore functional groups. This is through infrared spec. Then you would do, then you would look at the number of H environments and the number of carbon environments, and you could narrow it down that way. But you don't start with the mass spec, with the NMR. So this is NMR. Okay, so if we have a look at this question, question number 4, it says identify. The identity and molecular structure of an organic compound is to be determined using mass spec, NMR, and infrared. So first of all, this is mass spec, this is NMR, and this is infrared. So first of all, what can your mass spec tell us? Well, it has a relative molecular mass of 60. I didn't plan that, by the way. Okay. Your NMR tells us 3 environments, and your infrared spectrum says that, well, you guys got to know what these are. This is a CH, and this is an OH alcohol. So that's first just some preliminary work I do before I actually analyze the question, because it can lead me to the correct answer. So using these spectra, deduce the relative molecular mass of the compound. Well, we said it was 60. Identify any functional groups present in the compound. Well, it's got a hydroxyl functional group, which is the OH of the alcohol. Okay, it doesn't have an OH of a carboxyl because it's not overlapping the CH. OH of a carboxyl is lower energy. Number of different hydrogen environments, we said there are 3. Deduce the molecular formula. Well, there's an easy way to do this. You know that it has to have an O, so we could do 60 minus, well, you know it has an OH, so you do 60 minus 17, 16 and 1, and then you get 43. Okay, then you go, okay, I know it's going to have carbons, but we're going to work out how many. So I usually just do 43 divided by 12. And this gives me 3.6. I know that I can't round up because it can't have a higher molar mass than 60, so you always round down. So it's got 3 carbons. Then the rest have to be H. So let's add it up. 60 minus, we know it has 17 because of the OH, and 12 times 3 because it's got 3 carbons. And let's see what's left. 60 minus 17 plus 12 times 3 equals 7 exactly. So C 3 H 8 because of the OH, and then O. Let's see if that adds up to 60 to make sure. Perfect. Now here it says draw the structure showing all bonds for two compounds that have the molecular formula in B. So it has to be a hydroxyl. So it could be here. So it could be propan-2-ol, or it could be at the end, propan-1-ol. Okay. Then it says, explain how the NMR spectrum is consistent with only one of these, but not the other. Let's have a look at that. So it needs to have 3 hydrogen environments, and we have a look here. This one has, these two are in the same environment. So that's 1, 2, and 3. This one is 1, 2, 3, and 4. So we know that it actually has to be this one. But let's just check the peak splitting to be certain. You don't have to do this step, but I just want to enhance the explanation. Okay. So 1 is not split, so it has to be this one because the oxygen acts as a blocker. 1 is split into 2 peaks. So it has to be, oops, stuff that one up. It has to be this environment because this environment is attached to 1H plus 1, N plus 1 rule. And then this one is split into, it would be 7 because 1, 2, 3, 4, 5, 6. 6 plus 1 equals 7. Okay, so it does work out. So we haven't stuffed up our molecular formula or anything. Okay, explain how the NMR spectrum is consistent with one of the ones. So for this one, it's 2 marks. So you need to definitely say, discuss the hydrogen environments. And then you need to have 2 points. So you could say that propan-2-ol has 3 hydrogen environments which are consistent with the NMR. Propan-2-ol has 3 H environments which is consistent with the 3 peaks on the HNMR spectrum. And then you just say propan, because propan-1-ol could also have 3 hydrogen environments, therefore you'd need more evidence, but propan-1-ol, you have to also disprove the other one. So you have to prove this one and disprove. Propan-1-ol has 4H environments, not consistent with spectrum. Okay, then it says here, give the name of the compound to which all 3 spectra apply. Okay, so we said that above, propan-2-ol. Okay, now it says here, explain the presence of the peak at N to E, mass to charge ratio of 45. Let's have a look at that one. This peak is called the base peak. It is the tallest and it refers to the most stable ion. Okay, but let's see what it would be. Now, if we draw out our species, we need to cut it either here, 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 many different spots whenever there's a covalent bond to make that peak. Okay, so let's have a look. Okay, CH3 I know is 15 and it weighs 60 altogether, so that means that left is 45. So if you say what it is, you actually have to say the presence of the peak is due, doesn't really say in which direction, to the loss of a CH3 fragment. Or you could say due to the presence of a CH3 CHOH plus ion. Remember that the uncharged fragments are lost, and those are the ones that come up on the detector. So it says here the presence of a septet at 4. So we sort of said that before. So at 4, yeah, we said that the septet was because that CH is surrounded by 6 different hydrogens in the same environment. So you can just draw it out like so. You can always do this to really just exemplify which H you're talking about. So I'll just highlight it and I'd say this H is surrounded by 6 protons, by 6 neighboring protons plus 1. N plus 1, 6 plus 1 equals 7. Okay, now this one's a neat question, so it's a little bit more challenging, I'd say. Okay, so let's have a look. The mass spectrum of 1-butanol is shown below. Well, let's see if it's actually that. So, butanol is like so. I always like to draw it out first. Now, it's got 12 times 3 is 36. It's got a 16, and it's got 1, 2, 3, 4, 5, 6, 7, 8. It's got 8. So that is 12, 20, and then it's 6. Oh, I've done propanol again. Never mind. Okay. 6 plus 15. 60 plus 15 is 75. Okay. Now let's have a look to see if we've got that represented here. 74. Okay, because of that H, my bad. Plus 14 is 74. Okay. I don't know why I drew out propanol, but there you go. So once you add that up, it does actually, in fact, equal the heaviest peak, which is at 74. Okay, so they won't lie. Okay, now the second question says, in mass spectrometry, alcohols produce 2 characteristic fragments from the molecular ion by different pathways. Alpha cleavage, who knows what that is. It's not in the study design, but anyway, we like to do this. The C to C bond nearest to the hydroxyl group is broken, producing an oxygen-containing fragment. Well, the C to C bond nearest to the hydroxyl group is broken. So that's that one, producing an oxygen-containing fragment. Okay, dehydration, a water molecule is eliminated, leaving an ethene, an alkene-like fragment. Okay, that's a bit weird, but anyway. H2O, so that would be lost. So then left you would have okay. Now it says, give the molecular formula of the oxygen-containing fragment produced by alpha cleavage. Okay, so that's here, oxygen-containing fragment. So that's C1H3O. And that would be C1H3O plus. Okay. Now it says, on the mass spectrum, identify the peak of the fragment formed by the dehydration and mark it clearly with the letter A. So an easy way to do this is, whoops, sorry. An easy way to do this is you have a look at the molar mass and then you subtract a water molecule. So what you'll be doing is having 74 minus 18 is 54, 56. Okay, so that's 5246. Okay, and then A. So that's a kind of tall peak. Okay, now, next question. So it says the low resolution proton nuclear NMR, yeah. Okay, complete the table below according to how it will split. So, it says propanoic acid, so just make sure we draw it out. Now, propanoic acid has these 3 H's present there, these 2 H's there, and this H always very high energy, so I can already see it. Anyway, relative peak area, well, at 1.1 it's 3 to 2 to 1. Peak splitting, this is split into 3, is it? 1, 2, 3, yeah. This is split into 1, 2, 3, 4. 3, 4, 1. Okay, here. Examine the infrared spectrum below. Explain whether the spectrum shown is that of propanoic acid or 1-butanol. Okay, so let's have a look. It needs to be of propanoic acid because this is definitely an OH alcohol, but also it's got a C double bond here, double bond O. Now, I don't have my data book on me. Just 1 second, data book, because I told you have to use values, which is something you definitely have to do. Vika chemistry data book. Okay, here we go. So, first of all, you write propanoic acid, and then you'd have to provide those 2 definite signs of being an acid and not an alcohol. You have to disprove that it's an alcohol. So as soon as that loads, human. No, that's taking a very long time. Get my other laptop. Yeah, you just got to really make sure that you use values from your data book. Okay, so here we've got it here. Now, going down to infrared spectrum. Okay, so you'd have to say there is a broad peak at around, what is it around? Around 3,200. Which falls in the range of 2500, 3200 or 3100 even, falls in the range of 3 OH acids and not higher energy, and then you provide the value 3200 to 3550 OH alcohol. There is also a distinct peak at 2468 around 1750, indicating C double bond O, and then you give the value 1670 to 1750. Okay, so making sure you're really hammering in those marks. So it says here, draw the structural formula of this ester using these values here. Now it says same molecular formula as propanoic acid, so we know it's got 3 carbons. Now an ester could be one of 2 things. It could have, we know that an ester is made up of an alcohol and a carboxylic acid. So it could have the alcohol with 2 and the carboxylic with 1, or the alcohol with 1 and the carboxylic with 2. So we'll do both of those. Yep, or it could be like so. Now this one I'm crossing out straight away because that's only got 2 H environments, and this one has 3. 1, 2, 3. Peak splitting, I mean you already know it, but you know I'm just exaggerating it because I want to teach you a little bit behind it as well. But anyway, this wouldn't be split, so it'd be that one. If you just highlight which one's which, this, I can just tell by the peak splitting. This one's split into 3, 4. Why do I keep doing that? And this one, I'm making it the same sort of colour. This one's split into 3. So that's that one. And relative peak area 3 to 2 to 1. Okay, now it says here, name the organic compound used to produce this ester in a chemical reaction with an alkanol. Okay, so it's talking about the carboxylic acid, so it would be methanoic acid. Okay, so I hope that helped, and I think that you should be doing a few more of the combining technique worksheets that are available under VCAR questions by topic in this folder. Good luck.